this is kind of in some sense a huge problem with the whole field, that
Right.
the way you make progress is by experimentalists telling you that this part of what you think is true isn't working and you got to fix it. This in some sense is the fundamental problem with string theory. It's got this huge number of new degrees of freedom, none of which we see. It's got these 6 extra dimensions, none, which we see no evidence of. And so you have to, the whole subject then becomes about how do we come up with a theory of all this stuff, which also explains why we can't see any of it.
Hello, this is Robinson Erhardt, here with the introduction to Robinson's podcast number 224. And this episode is with Peter Woit, who is a senior lecturer in the Department of Mathematics at Columbia University, where he researches quantum field theory and quantum gravity. And this episode, if you've been listening to the show for the past few weeks, comes on the heels on some other big episodes focused on string theory, and these are with Raphael Busso and Leonard Susskind. And Peter is one of the most well-known critics of this approach to quantum gravity, so I knew he would be a terrific way to balance out that narrative. His work on the area, or in the area, are contained in his book, Not Even Wrong, as well as in his website by the same name, some links to which you will find in the description. But in this episode, we talk about our best theory of the microscopic, which is the standard model of particle physics, how physicists have attempted to move beyond it since its formulation in the 1970s, and then merge it with the theory of gravity, and this is called quantum gravity. Then we also spoke about the way that string theory has come to dominate this field, its many promises and potential shortcomings, and then the future of high-energy particle physics. Reviews, comments, likes, subscribes, always appreciated. There is a link to the Patreon in the description if you would like an ad-free RSS feed to ask AMA questions or to have show notes. And now, without any further ado, I hope that you enjoy this conversation as much as I enjoyed having it with Peter. Obviously, we're going to get to string theory eventually, but I think, as with Not Even Wrong, the best way to get into it is to start with the context from which it emerged. And I think there's no better way of doing that than asking what the world of physics was like when you were brought up in it and trained.
Yeah, and I've often been thinking about that recently, and the contrast between then and now, and it's kind of dramatic. So when I was an undergraduate at Harvard, and so I studied both math and physics, but it was mostly in the physics department, and that was a time that was really there'd just been this huge progress. So that was 1975 to 1979, and in 1973, 1974, it was the standard model had come together, and a lot of the people at Harvard, like Weinberg and Glashow, for instance, especially, had been the ones most responsible for this, and they had, so there were all these experimental results coming in, which were vindicating them, and all these kind of new theoretical understandings, which were kind of solidifying the whole story, and people learning new things. So it was a very, very exciting time, and it was kind of, there's just a huge amount of progress going on. And then I went to Princeton, and it was still, I think things were then starting to slow down. People were kind of realizing that, the standard model works very well, but there's the things that we'd like to understand. One thing we'd like to understand better is how the strong interactions really work and how so-called QCD works. That these were very much more difficult, much more challenging problems, and progress was going to be slow. And so that was what was going on then. And then when I left Princeton in 1984 and went to a postdoc in Stony Brook, that was kind of more or less precisely the moment that string theory all of a sudden kind of emerged, and Witten got interested in it and started promoting it, and things kind of changed dramatically then. So this period of when I was a student and up to the time I was a postdoc was a very, very different one than the years after that, which were really dominated by string theory and a much more problematic situation.
Well, the first thing pretty much you mentioned was studying math and physics
Yeah.
at Harvard, and a major through line of the story, not just of string theory, but of Not Even Wrong, is the play between math and string theory.
Yeah.
And I really hope to get into it. I think it's also interesting that one of the other major contemporary critics of string theory, Eric Weinstein, I think, is it Eric Weinstein or Steen? I'll go with Stein for now. He also did math at Harvard, and
Yeah.
it's just an interesting connection.
Yeah. So he has a somewhat point of view of that I'm sympathetic a lot with. But I mean, this kind of goes way back. I was always actually very interested in both math and physics, and especially in this kind of region between them, where mathematics is informing new ideas about physics, and physics is giving you some new insights into mathematics. That's always been what I've been interested in. So when I was an undergraduate, I was taking quite a few math courses. I even took some graduate courses in math, and even though I was mainly a physics student. But and that's kind of stayed with me the whole time. And I think it's a bit unusual that I'm not. Academia is normally pretty rigidly broken up by discipline, and kind of being kind of in between the two disciplines and being able to being kind of fluent in both languages is not that common.
I also just find Wigner's The Unreasonable Effectiveness of Mathematics to be quite interesting philosophically as well. And maybe, I hope we'll have time to get back to that and talk more about it. But I think next, another really good thing to discuss and spend some time on is what the standard model is, and not only what it is, but maybe the larger story of how it was developed and the role that experiment played in that, just because it proves a very good foil to string theory.
Yeah. Well, in Not Even Wrong, I tried to. There is kind of a standard story of the standard model. It's it's a fascinating history, but it's kind of a long story. In Not Even Wrong, I tried to tell that story in a little bit of a different way, not so much emphasizing experiment as emphasizing kind of the mathematics, that what physicists were learning about physics, and that things that went into quantum field theory and standard model, how those fed back and forth into things in mathematics. That was Wigner actually played a large role in that, and one of the kind of great heroes of the story, as far as I was concerned, was Hermann Weyl, who from early on was taught. He was a mathematician, a truly great mathematician, but who was talking to physicists a lot and was going back and forth. And he even wrote a book about quantum mechanics, which one chapter was math, next chapter was physics, next chapter was math, next chapter was physics. It's kind of an amazing document. And so that was, and that I was writing about that in Not Even Wrong, partly because that's a perspective on the whole subject, which I think to me is very important, which I personally find very important, and I think can be very fruitful, but isn't that common. But it's certainly true. Without without experiment, you never have anything like the standard model. It's got a fairly intricate structure. People would never just on their own have kind of come up with this. It had to be.
Maybe for our listeners who aren't aware of what the standard model of particle physics is, could you explain it? It's hard to explain the whole thing, but give a basic rundown of.
Well, it's really kind of our best understanding, really, of kind of fundamental physics, ignoring for the moment gravity. And so, and it basically says that there's kind of three kinds of forces. There's the electromagnetic force, the weak force, and the strong force. And they all, the really beautiful thing about it is you can write them all in terms of the same kind of mathematical structure. The structure is called based on what's called gauge symmetry. And so you just have, anyway, you have slightly different groups for these three things, but the way forces work is kind of uniform between these. And that's part of it. The other part of it is the theory of kind of matter fields, which are based upon spinor fields and the Dirac equation. And this, so this is an idea that goes back to the early days of quantum mechanics, and Dirac who wrote down kind of the first kind of relativistic theory that works. And there's the Dirac equation is also this kind of amazing piece of it has these amazing mathematical implications, but it kind of was discovered in physics in some sense. So you've got matter fields described by the Dirac equation, you've got forces described by gauge fields and gauge symmetry, and there's this one, probably the most mysterious aspect of it is the so-called Higgs particle, that it's some kind of field responsible for a phenomenon that the gauge symmetries, get in some sense broken and don't work in the way you would expect. The vacuum, normally when you have symmetries, you assume that the vacuum state, the state of the world, which is lowest energy, there's nothing there, that's invariant under all the symmetry transformations. Well, it's not true. The Higgs field makes that not true, that the SU2 gauge transformations kind of change the nature of the vacuum. So I don't know if that's helpful, but that's kind of a summary.
It is. Since you mentioned gauge symmetry, you mentioned just symmetry earlier, and I think supersymmetry will become very important, and then you also mentioned Hermann Weyl. Yeah. Do you think it is possible to give a lay briefing on the idea of what symmetry is in physics in these different, for now restricting ourselves to just symmetry and gauge symmetry?
Yeah, well, it's kind of hard, but in some sense, I mean, one thing I've done in recent years, I mean, it's kind of since writing Not Even Wrong, was I've been teaching a course here in the math department on kind of quantum mechanics aimed more at mathematicians, but aimed both at mathematicians or physicists, and the idea is to teach the standard kind of story about quantum mechanics, but from a different point of view, a point of view that would have been very much Hermann Weyl's point of view. Mm-hmm. Which is that, so the kind of amazing part of the story of quantum mechanics is that mathematicians during that time were developing these new ideas about symmetry, which kind of go under the name of Lie groups and representations of Lie groups. And these were things which were really, I can say a bit more about them, but the history is they really kind of became understood, and their significance for mathematics became understood during the 30s, 40s, 50s. But at exactly the same time, it turns out that those ideas are very much exactly the right thing for saying what's going on in quantum mechanics. Quantum mechanics has an unusual, to physicists, mathematical formalism, which looks very weird when you first see it. But if you know that kind of mathematics that Weyl was developing, you can see kind of a one-to-one mapping between these basic mathematical structures of quantum mechanics and the ones of the story of groups and their representations. So that's, I mean, the thing that most fascinates me about this whole story, and I was trying to tell some of that in the book, and it's also something which I think motivates me in the sense that I think there's still a lot that we don't understand about the implications of these ideas. We don't understand these gauge symmetries, what their representations are very well. There's a lot of the mathematics which remains undeveloped. And I do think one possible way to forward for this kind of physics is to a better understanding of that kind of mathematics. But just to say a few words about what it is, maybe a good idea to think of, if you want to think of, first is just to think of things called groups, and maybe a good example to think about is the group of rotations. So if you take, we live in three-dimensional space, but it has this kind of symmetry that if you kind of rotate everything about a point, nothing really changes. The laws of physics stay the same, and pretty much in the state of the world, I mean, it moves, but it's so this is one example of, you can think of what would be a symmetry, but symmetry is kind of an overloaded word. It doesn't. People use it in this context to mean somewhat different things. But maybe to be more precise about what's really going on, there are groups which are what mathematicians think of as Lie groups and think of the rotation group. There's an infinite number of possible rotations you can do in this three-dimensional. So it's a set of possibilities that have an infinite, but it's infinite and it has an infinite number of points. So that's a Lie group.
If you have maybe a sphere whose center is at the origin, any transformation that consists of just a rotation around the origin leaves the sphere sort of the state of the sphere is physically indistinguishable from how it was at first.
But this is where it gets confusing. I think it's better not to think about, when you're thinking about a sphere, you're thinking about something that...
Of course, it's abstract. It's not physical.
No. But you're thinking about something which, when you do a rotation, doesn't change it at all. So one of the meanings of symmetry is kind of invariance, that you act on something and it stays, and the thing stays exactly the same. But the thing about the world is that it, if you rotate this room around, it's not the same thing. It's not we're not in a rotationally invariant state. I mean, you see.
I feel like that's a philosophical. If the whole universe were rotated, is it the exact same? And then you need to appeal to some background lattice or something.
There's a lot. Anyway, there's a lot you can get into with this, but I just want to say that I think people often, to me, the kind of standard explanation to people about this gets confusing because people want to talk about. I think what they want to do is they want to define these groups by picking some thing that has a lot of, that the group can act on that has a lot of invariances. So they want to define the group of rotations is the group of all the things you can do to the sphere that leave it the same. But you can define the group without picking an invariant object like that. You can define you can just define rotations by, here, these are all, there are many ways of defining what the rotations in 3 dimensions are. But they don't, but what you're really, the thing is that you're interested in is you're not interested in just in things that are invariant under all those rotations. You're interested in a theory where the rules don't depend upon the kind of overall laws that you'd write down, your Lagrangian or whatever you want to write it down, stays the same. So your equations of motion, your rules, whatever you want to define it, those stay the same when you act. But the states don't. The states change. And if you pick up a square thing and rotate it, it's not invariant. And so what's interesting is not just the group, but the things the group can act on. And that's that's really what representation theory is about. This is what mathematicians kind of learned, was that the first interesting thing is there are all these possible groups. What are they? Let's classify the groups. But the second interesting thing is, given a group, what are the things it can consistently act on? And that's the representation theory. And the representation theory of a group turns out to be, far more intricate and far more interesting and have a lot more applications than the group itself. But this distinction between the group and the things it's acting on it's often kind of elided when people try and explain this, which is, I think it just makes it more confusing.
Mm-hmm. And how then does gauge symmetry build off of what we've just been discussing?
Yeah. So the symmetries of the standard model, so the world has some symmetries. It has kind of space-time symmetries, which are ones where the 3 space dimensions, the 1 time dimension, it's rotations, translations in space, translations in time. Those are called space-time symmetries. But what people discovered at some point as they developed the quantum field theory that went into the standard model was that what was interesting. There were interesting theories like electromagnetism where there was some kind of group acting, but it wasn't changing where you were in space-time. So it was at each point. One way of understanding electromagnetism is to think that at each point there's some kind of degree of freedom, which is kind of like a circle, and you have this kind of rotation about this circle going on, and you can do that and that's kind of independent. You can do this independently at each point, and that's gauge symmetry. That's the simplest example of gauge symmetry. And the idea goes back to Hermann Weyl, and even before quantum mechanics. He first came up with it and trying to get a different way of understanding, how electromagnetism and gravity might fit together. And then when quantum mechanics came along, it kind of clarified a lot what was going on.
Mm-hmm. Since you mentioned Hermann Weyl, one of the interesting things about the history is just how it seems like groundbreaking he was, but at the same time he wrote like a mathematician, which meant that physicists, it took a long time for them to really get into his work. And there's still a strange, well, it seems as an outsider, there's sort of a strange tension between math and physics.
Oh yeah. No. That's very much part of the story. Is that you've got people speaking. Yeah, I mean, they really have very different kind of histories and cultures and ways of writing and languages, and there's a huge barrier to move. Mathematicians have their own problems trying to understand what physicists are talking about. From a typical mathematician's point of view, the physicist discussion of something will just, will be so lacking in any kind of coherent or clear definition of what the person is talking about that they just, I just can't follow. I just can't deal with this. I can't follow it. A lot of mathematician friends of mine have told me, look, I started out wanting to be a physicist, and at some point, there's some physics course I took where I said, I just can't take this anymore. I can't figure out exactly what this person is talking about, and so I must be a mathematician. Mm-hmm. But and then mathematics is the opposite. Physicists just don't. They don't like the mathematician's insistence on rigor and everything being well defined, and there's just huge language barriers and not knowing kind of huge amounts of things which mathematicians are trained in that are necessary to kind of comfortably listen to them talk.
Mm-hmm. Something that's funny about the mathematicians being dissatisfied with the level of rigor that with which the physicists do math. What's funny about this is just that mathematical logicians, so set theorists, modal people who do model theory, they find that typical mathematicians are not nearly rigorous.
Yeah. There's different degrees of this. Yeah.
Mm-hmm. But okay, I'm really glad that we've got the symmetries and the gauge symmetries on the board. But the other part of the standard model that I think we really need to talk about is how it was informed by experiment, and particularly the role of colliders.
Yeah. So one thing I tried to do in Not Even Wrong was to kind of, again, to emphasize the importance of experiment and the importance for experiment of what experimental tools you have. And so the colliders are this most powerful and most recent tool that have been used to study the subject. And they give us, say by colliding at very high energies, like say two protons with each other, you're able to kind of access what's physics that's happening at very high energy scales or very short distance scales. But and so that's always been so if you try and track the history of the standard model, a lot of it kind of goes by this new technology or these new kinds of colliders or these new kinds of accelerators allowed access to physics at new smaller scales, and then you found unexpected things going on there, and that in some sense was the story until recently. I mean, one reason I think it's one of the main parts of the story of why kind of progress kind of in some sense came to a stop after the standard model, because
and that was around the mid-70s?
Mid-70s, yeah. Okay. So I would say it's kind of 1973 was when the final piece of it fell into place, and it took a couple of years for everybody to completely understand exactly what they had
and
there.
Start calling it the standard model.
Yeah, but probably I think even by the time I was in college, by the late 70s, people were already calling it the standard model. It had already gotten that name. Also, at the beginning, there were various slight variants of it. There were exactly the way the electroweak symmetries worked. It wasn't clear that the one that Weinberg had written down was exactly right. There were variants of it which were possible, but as the experimental results showed that exactly what it had to be. So, and I think it was kind of at the time that the experimental results showed that you could pinpoint this one particular choice for that. I think Weinberg and others started calling it the standard model.
Mm-hmm. And to what extent has it been experimentally confirmed? Just what does it mean to say that? Because we do know that it's incomplete.
Well, it's kind of hard to overemphasize. I mean, there really is there is no other example we have. I don't know anywhere in experimental science of a kind of model where you're in this situation where there literally is kind of there literally is really kind of nothing that people have seen experimentally that really is inconsistent with the standard model. And I mean, and this is kind of in some sense a huge problem with the whole field, that the way you make progress is by experimentalists telling you that this part of what you think is true isn't working and you got to fix it. And so nobody knows how to do that. So it's I mean, there just isn't anything out there. There's the kinds of things that people talk about, like dark matter or dark energy, are actually more kind of astrophysical or cosmological phenomena. And so those depend a lot on, what's going on in various galaxies and stars. And so there's a lot of astrophysics and cosmology coming into them. But if you are doing experiments that just look at the phenomenon this theory is supposed to explain, which are these matter particles and these forces, and every experiment you do, it comes out right on the nose. And that's, I mean, trying to think, but and that's, I just don't know of anything else like that anywhere else in science.
Right, I agree that it can't be overemphasized, the problem that science has going forward, given just how successful the standard model has been with explaining all observed phenomena at this small distance scale. Yeah. But what still needs to be recognized, or what we still have to talk about, is why, if it can account for all of this phenomena, it's wrong or it's incomplete. What are its major problems?
Yeah, so I think the So one problem, the problem people mostly emphasize is that of gravity. That it doesn't kind of tell you. It's perfectly consistent with a kind of a classical description of gravity. But if you then start to do thought experiments about what if you could do an experiment at a scale where you could see quantum effects of gravity, then the standard way of kind of applying quantum theory to Einstein's equation gives you some inconsistent, is not quite consistent, so you got to do something about that. That's the main thing everybody emphasizes and is motivated. Most of what people do. I think it's also more important to realize, though, that the theory, just looking at it, seems to be very incomplete in the sense that it doesn't. While it's giving you accurate numbers, it's telling you how to calculate things. It's kind of not, there's a lot of things that just doesn't seem to be explaining what you think a truly fundamental theory, which is supposed to really capture everything that's going on, should tell you. And one aspect of this is that, for instance, it says there are all these different kind of fundamental fields and particles. There are quarks, electrons, muons, tauons, et cetera, and they all there's a different mass parameter for each one. So there's this very, very long list of these mass parameters, and they're just a bunch of random numbers, and you have to put them in by hand. And if you look into the theory, they in some sense these numbers measure how strongly the field describing the particle interacts with the Higgs field. And but why this completely weird random set of numbers? And then there's also, kind of somewhat larger structural things that for instance, you've gotten these three forces, and they're described by gauge fields of the group U1, SU2, and SU3. So why 3, why U1, why SU2, why SU3? And so a lot of effort has kind of gone into, I think so far fairly unsuccessfully, into trying to come up with an improvement in the standard model that would actually answer some of those questions. Mm-hmm. But that really just kind of has not successfully worked so far.
Just to recap, to make sure that I'm on the same page, the three major problems you've identified are that it's inconsistent with the quantum theory of gravity. Yeah. It does not explain where the free parameters of the model come from.
The three forces, yeah.
Well, not the three forces. I just mean the free parameters in general.
The free parameters.
The free parameters.
Yeah.
And then there are these larger structural features, such as the symmetries, where they come from.
Yeah.
Okay, those are the main problems. That's good to know. And the next thing then, before I think we get to string theory, ought to be how physics progressed after the standard model was adopted, and what I have in mind are grand unified theories.
Yeah. Well, I wouldn't I wouldn't call it progress. That's the problem.
Okay.
Yeah. So grand unified theories are, yes. So I think one thing that's remarkable to look at the history is some of these ideas about how to go beyond the standard model came up like months or a year or two after the standard model base. So I think grand unified theories are like 74, 75. And there the idea was, well, mathematically you can take, U1, SU2, and SU3, and you can make them subgroups of a bigger group. Let's say, for instance, one called SU5, all kind of complex 5-dimensional transformations. And then you can write down a theory that has this bigger symmetry, and you could say, well, the reason that we see these is because instead of having these 3 different things to explain, there's really only kind of one thing. And so we have an improved explanation. The problem with all these grand unified theory schemes, though, has always been that they, while you kind of reduce the number of basic objects to 1, you don't actually have an explanation of what breaks the symmetry back down to U1 cross SU2 cross SU3. So if you try and do the standard grand unified theory thing, you say, well, instead of 3 forces, there's 1 force, it's an SU5 force, and there's only 1 parameter governing it. But we have to introduce a new and different kind of Higgs field, and we have to tune all of its parameters so it does exactly the right thing to break the SU5 down to what we see. So you've just traded, you think that maybe you've improved matters by getting rid of 3 things and making them 1 thing, but it's 1 thing together with a complicated package explaining how you're going to get back to the 3 things you knew about before. And that's in some sense always been the problem with grand unified theories. And so conceptually they weren't completely convincing because of that. And then the reason people got most excited about them is that they carried certain kind of experimental implications, that you should have quarks should decay, then you should be able to go from quarks to leptons, and protons should decay. And then people went out and started doing very precise measurements of the proton lifetime and find out that protons don't decay. So I think even the people who most were, started those theories, got most excited about them at the beginning, people like Georgi and Glashow, I think they later in life kind of gave up on them, saying, once they saw that the experimental results were in, and what the experimental vindicate, they were hoping that it would vindicate them, they'd get a Nobel Prize, but they kind of accepted the matter that, okay, experiment says this is not the way it goes, and they moved on to other things.
Yeah, well, that last point is actually what I thought was pretty crucial, because even though you didn't want to qualify the work on GUTs as progress, they at least followed the standard scientific method, and that they were falsified by experiment, and they were left at that.
Yeah. So in some sense, that's true. I mean, I think the more disturbing thing about them is, I think a lot of the story that people tell the public about that is people say, well, we have here's a standard model, and we have these great ideas about these grand unified theories, and aren't they wonderful? And you kind of don't tell people that there's far too much like of not telling the people that, oh, by the way, this idea doesn't actually seem to work. I mean, it actually doesn't really explain as much as it seems to, and the experiments say it's wrong. So there's a lot of kind of still I think you'll have, like, people in graduate courses will teach students about, here's how grand unified theories work, and why are we teaching our graduate students about grand unified theories? They don't. It's an idea that doesn't work. So there's this kind of there's a milder problem of the problem, which is kind of becoming very serious in the whole field of kind of refusal to kind of distinguish between ideas that don't. Once it's clear that ideas that don't work, admitting that, and that's become to me a really huge problem for this subject. And the grand unified theories are kind of an edge case of that.
Mm-hmm. Well, again, we'll get to the contemporary situation, but there are two things that I want, or a couple things that I want to talk about before we get to that. The first is one other symmetry that we haven't talked, or type of symmetry that we haven't talked about yet. So we talked about symmetry, we talked about gauge symmetry. Yeah. What is supersymmetry, and how did that emerge in the wake of the standard model?
Okay, so it's a somewhat similar to grand unified theories. Its story is actually very similar. And again, it was also, a year in 1974, like a year after the standard model, people had first started writing down these supersymmetric theories. And there it's the mathematics is somewhat similar. It's just that the super means you have to combine kind of bosonic things where your variables commute in a normal way, and kind of fermionic things where your variables anti-commute. That it's basic part of the story that, anyway, there's some degrees of freedom that are fields that behave normally the way you expect. They commute. There are other ones, the ones that describe matter, that they anti-commute. And so what people had realized is that if you start this whole mathematical package of Lie groups and representations, that you can have super Lie groups. You can put, if you at the same time think about our normal kinds of functions where the functions commute and these anti-commuting things, you can put them together and get kind of a super version of all of this mathematics. And one thing you can then ask is, well, a fundamental part of the story is what people call the Poincare group, that you can translate in three space dimensions or in one time dimension. So you have four kinds of translations, and you can do rotations in 3 dimensions, and then special relativity says you can do transformations that combine space and time, these so-called Lorentz boosts. So there's this group of all these things called the Poincare group, and its representations govern very, very much what the possible particles are and how they're going to behave. So what people had realized was that you could take the Poincare group and make something bigger, including these fermionic degrees of freedom, make a super group out of it. And so it's very much like the grand unified story. You were starting with this smaller set of 3 groups and trying to make one big group out of it. Well, here you're taking this group and you're making something bigger. And whenever you have a bigger group, you have more relations and you have more things. In some sense, it explains more things. So you had these supersymmetric theories that people started writing down, and they had a lot more structure you can play with than the standard theories, and it's a very interesting structure. But they in some sense have exactly the same problem as grand unified theories. The problem is that they're too. we don't actually see that the new symmetries that they say should be there. We don't see. So they for instance say that for every particle there should be it should have something called a super partner. It should have another particle, and that the symmetry transformations move you back and forth. And then now if you looked at the real world and you look at all the degrees of freedom we know about, all the particles we know about, none of them have super partners. You can't you can't use the symmetry to kind of relate two different things we know about. So you do something, which is where the whole thing starts to become problematic, is that you say, okay, well, maybe the world really does have the supersymmetry, but every particle we know about, every degree of freedom we know about, there's another one, the super partner, and it's just we haven't seen it yet. Mm-hmm. And but then you have to start going into contortions to explain why haven't we seen it yet? Well, it's very massive. It's too massive. We haven't seen it yet. So you're then in the same problem as with the guts. You've told us about this beautiful, wonderful new symmetry. It's going to do all this great stuff, and then you say, but in the real world, you don't actually see it. So you have to. The thing has this beautiful supersymmetric theory has to come with a whole package of these new kind of super Higgs fields, which are going to break it and explain why you do what you see. So you've kind of lost any, and that's the fundamental problem with supersymmetric theories. It always has been. They kind of don't really predict anything, because what they do naively predict you don't see, so you're assuming that you're working with some more complex version of them where there's a complicated thing going on keeping you from seeing that, and then it starts to become hard to say anything. I mean, though there is, anyway, but there's a separate story about what people were hoping for about the LHC and that whole story, but that's the overall problem.
Yeah, and hopefully we'll get back to super partners in the LHC and string theory soon. The last person, or the last thing who happens to be a person that I wanted to talk about before we get to string theory is not Leonard Susskind, who I mentioned before we started. I spoke to quite recently because, I mean, he is integral to string theory. But I wanted to talk about Ed Witten, because you write about him at length in your book, and he's a tremendously interesting character. Something that I found quite fascinating while I was reading your work was this I do not think is fair. He's not your enemy by any stretch of the imagination, but it is still funny to see how glowingly and admiringly you write about his technical ability and his physical intuition when he's a string theorist.
Yeah.
I think that was just interesting to read.
Well, anyway, there's a lot to say about him, but he's I mean, I think he personally and his own choices and his own talents, have just had a huge effect on the subject since, starting around the time when I was a student. I actually met him. Can you tell
his story, like who he is, just for people who don't know who he is and where he came from?
Yeah, so actually, his father was a physicist, and so I'm a Lewis Witten, but so where to start with this? I mean, he didn't actually start out studying mathematics. I think he had studied a lot on his own and learned a lot about it, but he majored, I think, in history, and he was studying history and economics and thinking of working as a journalist or in politics, and then at some point I think he realized that his true talents lay in the field of his father, and he then came to Princeton, and I think he was actually admitted not in the physics department but in the applied math program, but then immediately started working in the physics department and working with David Gross, and this was just a couple of years after the Standard Model had fallen into place. So there was a huge amount of work going on of people trying to understand the implications of the Standard Model, and Gross had been one of the ones most responsible for that. And he he's just anyway. If anybody's a genius, Edward is a genius, and so and I even remember talking to people who were there in Princeton at the time as a student, and one of them told me, he ruined an entire generation of physics students there because they saw this guy come in who didn't really even know that much about the subject, and within a year or two he knew far more than they did and was doing all this amazing stuff. So they figured, I must be an incompetent, and so that's somewhat of a joke, but he then went on he became a postdoc at Harvard, where I first met him. He actually agreed I was looking for somebody to do a reading course with, and I would go and talk to him so often. He explained some things about quantum field theory to me, and he was he's just a truly remarkable person. And I then went to Princeton as a graduate student. He became a full professor at Princeton, I think a year or so after I got there. So anyway, if you know the subject, you know that going from being a graduate student to being a postdoc for a couple of years to being a full professor at Princeton is not the way things normally go. And I think most people think the biggest mistake the Harvard physics department ever made, and was not doing everything to keep him there and not making him a full professor and making sure he stayed at Harvard. But then, while I was at Princeton, he was just doing amazing things. He was just kind of revolutionizing the field and all these.
In quantum field theory?
In quantum field theory, just within the Standard Model mostly. He was just, the big problem was really, how do you understand these strong interactions? That we didn't have any good calculational tools for understanding strong interactions. And he was just coming up with these amazing ideas about how to think about the strong interactions that within the context of the Standard Model, which just were kind of revolutionary and involved he was bringing all sorts of new mathematics into it. He was spending a lot of time talking to mathematicians, and like Michael Atiyah, and he was learning a lot of mathematics. So it was these kind of writing these beautiful papers, amazing mathematics, amazing new ideas, and serious connections between physics and math. And I mean, he just had, everybody was just looking at this in amazement. And then I went to, became a postdoc, and then I heard that later that fall that Witten has gotten very interested in string theory, and he's now telling everybody that he's started writing papers. He's working full time in string theory. He's writing papers on string theory, and he's telling everybody, that this is really the greatest thing in the world. And pretty much every postdoc I know who's a friend of mine at one point had told me a story of, I went down to Princeton to talk to Witten about what I'm doing, and he told me, that's very, very nice, but you really should be doing string theory because that's what's happening. So that's, I don't know if that, the story kind of goes on. That's kind of the beginning of it. But the later parts of the story that I tried to tell, and not even wrong, are often about, in between working on string theory, he also just had these revolutionary ideas about the relationship between quantum field theories and mathematics, and so-called topological quantum field theories. So he ended up, completely revolutionizing one area of mathematics. Four-dimensional topology was just kind of completely blown apart by these new ideas that he brought into it. And so over the years, he was just doing these amazing things. But then he was also working on string theory, and I have very, very mixed feelings about that period. On the one hand, he was doing these things I think are the most spectacular thing that no one else could have done, ideas that I think are beautiful and truly love. On the other hand, he was pursuing this idea he was in love with about string theory, which I really think was just not working. And,
There is this very funny passage in your book. I thought it was funny. I liked it. Where I think maybe you were visiting Princeton or something like that. You were following him up.
Oh no, we went as a student. Yeah. It was meant kind of as a joke, but to give that idea of, and it's actually a true story. So if you know Princeton, there's the physics department and there's the math department. There's this plaza in between them. The library's underneath, and you come out of the library, you come up a stairwell, and then you're in the middle of the plaza, and you can go either physics. And so he was a little ways ahead of me, and kind of went up the stairwell, and then I got up the stairwell, and there was no one there, and it was kind of quite a ways to either one of those buildings. So I was then joked to people to look. I think he knew, he didn't think anyone was around, so he just teleported from one place to another. And but it was certainly intended as a joke. I don't actually think he's a Martian alien, but he's definitely clearly someone able to do things that none of us knew anyone else who could do.
Mm-hmm. Well, last Witten question. This is just something I'm personally curious about. I've done something like 220 interviews for the show. I've interviewed some very accomplished scholars in their field, but some of them, just from talking to them, you wouldn't know that they have this totally genius mind. And I'm wondering if in just conversation with Witten, you can tell that he's thinking on a completely different genius level, or if it's something that just more comes out in his work.
Yeah, no, I think it's, no. Yeah, he's actually, yeah, I would say it's definitely something in his work, though. But certainly in the sense, just listen. There's some of his talks I've been at, and were just these amazing experiences just to see that. But just if you before, anyway, he's an unusual person in some sort of ways. But there are things you can say about that, but they're not. Those unusual personal characteristics don't really. Anyway, those don't immediately say, "Oh, this person must be a genius." They might.
Mm-hmm. Okay, well, this has been a very lengthy prelude, but I think we're ready to talk about string theory now. I think talking about the background is really important, though. So, just what is string theory, or what does string theory purport to be? How is it explained in, popular media, and what is the problem that it's supposed to solve?
Yeah. So. Actually, so the history of the theory actually goes back to So before 1973, when Gross and other people figured out how to understand the strong interactions, there were this alternate approach to try to understand the strong interactions, which wasn't very successful. And actually, Lenny Susskind was one of the main people doing this kind of thing. And what people realized is some of the models they were trying to play around with, which they hoped would explain the strong interactions, you could think of them physically as that instead of quantizing a point particle, that you've got a particle moving around and it's at a point, and you've decided to treat it quantum mechanically, that you had some kind of infinitely thin kind of loop of strings, some kind of one-dimensional loop, which classically could be, maybe you could think of as a taut string that can vibrate in various modes.
Was it a closed loop at first?
Well, it's both. You want to talk about closed strings, and you also want to talk about so-called open strings.
Right. I'm just wondering if the earliest pre-string theories involved a closed loop or an open loop.
I guess the theories that you were, you were in some sense...
Like they came out of Veneziano's, if that's how you pronounce it, his work. I imagine it would be an open string because closed strings correspond to...
Well, it's... I think that the problem, the thing is, you kind of need both, and but the simplest theory, it's really just kind of a question of mathematically. Do you look at kind of, you've got a circle little thing, and do you look at kind of, do you think of that as like an interval with periodic boundary conditions that you've identified the boundary, or do you actually, make some more assumptions about an independent assumption of what's happening at the boundaries? But it's kind of the same question of how you've got this object which has an infinite number of kind of possible vibrational frequencies classically, and whether they're on an open loop or an open string or on a closed loop. But so then each of those vibrational frequencies, you then say, okay, there's going to be I'm going to quantize that, and so you've got you've got a new physical system you can think about, and and the idea is that when these strings are very, very small, that this should reduce to back to your point particle case, and so people had tried to study the strong interactions with these models, and some things it kind of works for, but mostly it doesn't work. But then after the standard model came in with a very different and completely and much, much better explanation of the strong interactions, a few people who were quite devoted to these theories kind of kept on working on them, and they thought, what else can we do with this theory? And one idea was to try to identify one of the vibrational degrees of freedom of this thing with a graviton and use it as a quantum theory of gravity. So there were people throughout the late 70s working on that, and I know that Witten was always, I think, kind of interested in this, but he wasn't very. I think he saw technical reasons that this was probably not going to work out, and then in 1984 there was this technical development about this, which which convinced Witten that the thing which was bothering me about these kind of theories technically is actually not a problem, that work, and that's why he all of a sudden became quite devoted to them. I'm not sure that really is enough about.
So that's the discovery of string theory, the realization that it could serve as a quantum theory of gravity, and then is 1984 the first string-theoretic revolution? Yeah,
so that's when. So until then, there really weren't. There was just a very small group of number of people on this working on it, and then there was kind of a phase transition. Within a few months, you had a sizable chunk of the community was starting to think about it and work on it. Yeah.
Mm-hmm. And then one other key development, I think, is the second revolution. Maybe we should gloss that before moving on.
Well, that's... Yes, it's maybe to tell him in my own version of the history of string theory, and is that maybe it's also a good idea that also to say kind of what this picture was. So I think Witten. So I spent a lot of time trying to understand, knowing Witten and knowing what happened. Why he to this day says he still thinks this is a great idea and this is the most promising thing. People should still think about it. And while he doesn't know how to make more progress now, it's still, this is just this most fascinating thing. And why did he so fall in love with this idea? And to say specifically, there was a specific version of the idea that he and a lot of other people fell in love with in 1984, which was that there are these technical calculations of the kind that he had thought were a problem. Those show that that if you try and make sense of the string theory, you can't do it in 3 space and 1 time dimensions, but you can do it if you have 9 space and 1 time dimension. So that is kind of uniquely picked out. So this is a theory which, at least the simplest versions of it, only work in 10 space-time dimensions. So, and there's one thing that continually kind of annoys me is when people say, oh, string theory is this known to be fully consistent theory of quantum gravity, it's great, and that's true in 10 dimensions. You really only, all these claims about the consistency of string theory are about string theory in 10 dimensions, and we don't live in 10 dimensions. So you had to explain what are you going to do with the other 6. And one of the things that I think only Witten could have done is to understand to start thinking about the mathematics of what to do with the 6 dimensions. So one obvious, the main thing they're doing is, well, let's assume there are 6 dimensions, but they're very small, so we don't see them. And anyway, he came up with various consistency conditions about what the 6 dimensions would have to satisfy in order to get supersymmetry to work out, actually, and to get various other things that people would like to happen. And so this was these so-called Calabi-Yau manifolds. And initially, the people got very excited. There was a lot of interaction between physicists and mathematicians because mathematicians knew only a few examples of these Calabi-Yau manifolds. And so physicists learned that, and they said, okay, great, we just have to find out from the mathematicians what the few Calabi-Yau manifolds are. We just got to find the right one that looks like the real world, and then we're going to have this theory of everything. So that was kind of the dream of 84, 85.
So the idea was that in order for string theory to be complete, it needed these 6 extra dimensions, and what Witten figured out was they could be made compact into the form of these very complicated Calabi-Yau spaces, where at each point in space-time there's sort of this tiny, very complicated Calabi-Yau space in which the strings can vibrate and move around.
Yeah, and you really needed somebody like him who, the mathematics of this is quite complicated, and in 6-dimensional Calabi-Yau manifolds are a complicated story in algebraic geometry, and so having somebody who could understand that story and feed it back and try to use it in physics was him. And I should say, my reaction to it at the time was quite skeptical, and exactly for the same things that I was saying about grand unified theories and supersymmetry. I mean, you're telling me, you have this wonderful new theory which includes everything, and it's got all these great new symmetries, but it doesn't look like the real world. It's got all this other stuff in it besides the real world, and you then have to start going into more and more contortions about how you're going to get rid of that stuff, all the extra stuff, and get back the real world. And this, in some sense, is the fundamental problem of string theory. It's got this huge number of new degrees of freedom, none of which we see. It's got these 6 extra dimensions, none, which we see no evidence of. And so you have to, the whole subject then becomes about how do we make this stuff, how do we come up with a theory of all this stuff, which also explains why we can't see any of it. And it's kind of a dubious, anyway, it's not at all convincing. So I never, this is why I never understood Witten's love affair with this theory. I mean, it just didn't, and people's talk about how beautiful and wonderful and elegant, et cetera, this thing is. It's just, well, no. I mean, it's kind of a mess. But anyway, so that's pretty much the story of what happened after the first string revolution. And then then there are later developments, but I would say, by 3 or 4 years after, by the early 90s, people were starting to get to be like, wait a minute, this is kind of a mess. It doesn't really work, and there was starting to be some skepticism. But then there's the next step of the theory, which we want to talk about.
Mm-hmm. Yeah, well, we can get to that second revolution in a moment. Just something that's worth noting or reflecting on for me is, as a non-physicist, there is so much. I mean, you would probably call it propaganda. I don't want to call it that because I want to be impartial.
Normally, say hype is what I call it.
Yeah, okay. There's a lot of hype around string theory, and there are a lot of evangelists for string theory. I imagine much less now than there were 10 or 20 years ago.
No.
Okay.
Anyway, we should get to this. But I think the current situation is actually much more disturbing than it was back then.
Okay. Well, yeah, we'll get to it. But what I was just going to say is, as a non-physicist, hearing it trumpeted over and over again that there are these 6 extra dimensions, it at first seems very weird, but then I just sort of like take it for granted because I've heard it so many times from all these authority figures. And it's interesting to put myself in the shoes of somebody who's actually much more familiar with this and how crazy it sounds to them.
Yeah, well, yeah, I mean, people at the beginning, people you have a very speculative idea. Maybe it's crazy, people fall in love with ideas for all sorts of reasons. And I think my initial reaction to it was, well, I don't think that's going to work out, but maybe. But I also thought that it would follow the pattern that all such things happen. Is that people would get excited about an idea, they look into it, and then if it didn't work after a couple of years, they'd move on to something else. And the truly bizarre part of the string theory story is that we're still here 40 years later, and why didn't people 3 or 4 years why didn't people in the late 80s or early 90s say, okay, well, this isn't working out, we should just give up on it, move to other things. That's I think the really hard thing to understand about this story.
Mm-hmm. Okay, well, maybe the last point in the history, though, is that second revolution that I think took place around 95.
Yeah, 94, 95. And so people, that starts to become a lot more complicated. So what people, maybe one way of saying it is that the other problem with string theory from the beginning is that it never was a fully defined theory, that you don't, you only really had a consistent theory you could write down for what kind of so-called weakly coupled strings work. So maybe a way to say it is that if you have 2 of these vibrating strings, if they interact with each other only very weakly, that there's only a very small chance that they'll affect each other. And in the limit, as that chance goes to 0, you can do calculations and you can say things. You don't have what we would call a non-perturbative theory. And so one of the big thing, and this is what Witten, I think unsuccessfully, even he would agree, spent huge amounts of time thinking about how do we come up with a better version of string theory, something that really is consistent, and that would make sense also for these strongly interacting strings. And what people were finding was that there were, if you look kind of at open strings and you started thinking about the possibilities of what could happen at their endpoints, and you started thinking of what could happen at their endpoints as new degrees of freedom, you could have things called branes, and you could have an elaboration of the theory which had all sorts of interesting properties, and what Witten and others realize is that in these so-called brane theories, those had extra kind of interesting symmetries, that theories with one kind of branes were related to theories with another kind of branes. So there's some extra underlying structure there, which was kind of unexpected. And so Witten in 94, 95, whatever it was, he then came up with this kind of M theory hypothesis that there is all of these different things we've been looking at are all related, and there's some underlying theory called M theory, which in the limits gives us these different things that we've been seeing. So it was kind of it was an organizational principle about the things that we're seeing, which led to a lot of predictions about the mathematics and about how these different theories were related, which was there's a lot you could do with, and that was very useful. But it also came with this kind of philosophical idea that there is this one underlying that string. There are not just several kinds of string theories we knew about. There's only one kind of a string theory, and all known string theories are limits. But I mean, anyway, so those were the words that were said then. Those were the words people are still saying. But there just wasn't a lot of evidence. It was always more of a dream and a hope than something that actually existed to this day.
Okay, well, good. Now we've got our context, we've got the background on string theory. I'd now like to turn to more of the problems with it, or your criticisms with it. And I think M theory might actually be a good place to start, just since we're here right now. So the problem one problem you identified is there wasn't just one string theory in 94, 95. It was conjectured that the 5 string theories and then supergravity were all limits of one larger encompassing theory, M theory. And what has come of that in the last 30 years now?
I mean, I would argue nothing. I mean, there is no M theory. I mean, every attempt to write it down just doesn't have the properties that you want. I mean, you can, for a while there are these kind of matrix models people had you, so you can still write down some theory involving infinitely large matrices, but it only kind of works in some very limited cases. And I mean, I don't know. It's a little bit. It's kind of hard to criticize this because there's not. I mean, there literally is no. This is something which I think it took me a while to actually realize. When I was watching the people doing this, I thought, okay, well, these people must have a fairly clear idea in their mind of what is kind of unifying these things, what's causing this, and no, I mean, they had some hopes of ideas that might work out, but none of them ever worked out. So, I mean, M theory has always just been this speculative postulate of a theory which no one's ever found, and which, when very, very smart people have been trying to do something for 30 years and never getting close to, and everything they do just doesn't work, the obvious explanation is that there just isn't. There isn't, my guess is, there are interesting structures there, which could give you more insight into some of these patterns people were seeing, but they're not. Those patterns and those structures are not actually anything useful for physics. So those are not going to do. So if you're pursuing this, looking for something that's going to look like physics, you're just doing the wrong thing.
Mm-hmm. And I mean, a string theorist that I recently spoke to, I wanted to talk about M theory just because, I mean, you don't even need to get into M theory to talk about dualities because there are dualities elsewhere in physics, but I just find the web of dualities quite interesting. But he told me, I don't want to talk about that. It's boring, and there hasn't been any progress on it in 20 years, so we're going to have to talk about something else. You won't be able to keep me on this subject. And I found that very interesting, and it raises the question, what string theorists have been doing in the past 20, 25 years?
Yeah, that's an interesting question.
Because I'm interested in dualities, I'm very interested in the ADS-CFT correspondence, and that I think was 97, then Witten had this big paper 2 months or so later in 98. These are two of the most cited particle physics papers of all time, something like 20 and 15,000 citations, something in that neighborhood. So it has been the source of tons and tons of work over the past 20 years. And I'm wondering if you think, even though M theory hasn't really progressed, this has been fruitful work.
Yeah, so one answer to what people are doing is exactly ADS-CFT, and so that's just an example that's not an M theory or whatever. That's more of an observation that
maybe since I didn't explain it, could you say just quite briefly what it is?
Okay, so maybe to say what it is so as you were saying, so a lot of the story about brains and what had happened with people thinking about brains and strings was realizing that there were certain kind of patterns to these theories, which these dualities, which gave you some interesting structure where you could then relate two different kinds of theories and use them to understand each other. And so one of these dualities, which I figured out, was this so-called ADS-CFT. To relate it to string theory, you would say if you take your strings in 10 dimensions, and then you don't make 6 of them small, you make 5 of them small, and then then you've got five other ones, and then it turns out that you could study a version of this theory where those 5 dimensions had the structure of what's called an anti-de Sitter space. It's a 5-dimensional curved space that is kind of infinite. And then as you go farther and farther out, there's basically a 4-dimensional sphere of kind of directions to go out.
One of the crucial points about anti-de Sitter space, though, is that it's got negative curvature, which is not the curvature of our universe.
Yeah, but it's also the wrong dimension. Again, I mean,
true.
There's the whole problem with all this stuff is people love to talk about, string theory is giving us this great understanding of gravity, and but it's the wrong dimension. And so it's to the extent that this is telling you about, you want to interpret. So then what people realize is that if you think about strings moving around in this 5 dimensions, because you've gotten rid of the other 5, and then you think about them kind of, as you go off to infinity, you imagine that they have n points at this going out to infinity, then you could relate what's happening on this kind of large 4-dimensional sphere at infinity and this 5-dimensional curved ADS space inside where the strings are moving. So the statement is that of ADS-CFT is that string theory in 5-dimensional anti-de Sitter space is related by this duality transformation to this conformal field theory of a Yang-Mills type, of a supersymmetric Yang-Mills type, a specific one in 4 dimensions. So you could kind of hope. The great thing about this idea, you could hope to read it either way. You could hope that since you actually know something about 4-dimensional quantum field theories, you could use those. People said, "Oh, now we can use those to solve this problem of how to define our string theory." Because we didn't really know how to define the string theory non-perturbatively. Well, if it's dual to this 4-dimensional quantum field theory, which we understand, then we're good. We have a handle on it. So that was one direction. And then, but then you also could try to read it the other way and say that, well, the string theory, where the strings are weakly interacting and where we understand them, is going to be related to this 4-dimensional quantum field theory, where the quantum fields are strongly interacting, which is actually hard to understand. So we can use string theory to solve problems in quantum field theory.
So it's very useful because it's a strong weak duality.
So those were the two ways, and I think the hope that you can actually, so people were actually hoping you could even kind of solve the problem of M theory. You can get a non-perturbative string theory through this duality, and that I really don't think that's worked out. I mean, because it's not. Anyway, it's not really a definition. It's kind of because you don't really know how the duality is going to work. So you're just saying that I define the problem away by saying non-perturbative string theory at large coupling is this quantum field theory, but you don't know how the mapping goes, so you haven't solved that problem. A lot of the excitement was in the other direction, was that people thought, okay, well now we have a new tool coming out of string theory which can be used to study strongly coupled quantum field theory problems like the strong interactions. And there was a lot of hope at the beginning that this idea would actually allow you to do calculations in the strongly interacting theory of QCD. And people worked very hard on that, and there's a reason why that doesn't really work. But I think the way it kind of evolved then is that the thing that people most took out of this was the idea that we can study strongly coupled quantum field theories of a kind that we normally know about in either QCD or one from condensed matter physics or from any other theory, and we can relate these to this 5-dimensional theory, to this theory in 1 dimension higher. And very often you find that it's not actually the strings that are relevant, because you end up being interested in actually what happens kind of at lower energies, where the strings are supposed to kind of give you a theory of gravity anyway. So the actual thing that people study is kind of what they call gauge gravity duality, which is just a gravity theory in 5 dimensions and a gauge theory in 4 dimensions. So in most of the work that people now do in that, the strings are long gone. So the strings were kind of the motivation for this, but anyway, so that's been a huge topic since '97, is this gauge gravity duality and what you can get out of it, and there's a huge amount you could say about that. There's also been a huge amount of hype about it. A lot of the claims people make about how this is going to revolutionize physics, it doesn't really work out, and it turns out to be that you never really understood exactly how this mapping is supposed to go. So there's something going on, but exactly what it is still not clear. And so people are spending a lot of time. But one thing that people with string theorists have done is spend a lot of time looking at this gauge gravity duality, but in lower dimensions. You say, let's try and imagine what would happen if we had like a two-dimensional gravity and a one-dimensional boundary. And how do we relate the theories in 2 dimensions and 1 dimension? And then you all of a sudden have things you can do a lot of calculations with, and that's been a big effort.
Mm-hmm. Do you think? I mean, one of the reasons that it was there was so much hype about it was that it was a concrete realization of the holographic principle. Though, to what extent you want to label it concrete, since it's not our world, is another matter.
Yeah.
And so, string theory aside, you mentioned that strings are long gone, or from the study of gauge gravity duality, at least in some respects. Has this whole field of research still been useful for furthering quantum gravity? Or do you think because quantum gravity is so dominated by string theory, it hasn't been that useful?
Well, I think the problem, in my mind, what people have done is they've kind of decided that, okay, we don't have a specific. I mean, the only case where we really know in any specificity of how to do this is 5-dimensional ADS, so is in the wrong dimension, wrong curvature.
Right.
It's completely unphysical. So if we try and do it in 4 dimensions and, no scalar curvature or positive curvature, then it doesn't work. So there've been huge amounts of efforts trying to make it work in the right dimension. This idea just doesn't work in the right context. It's a standard example of kind of what's happened with string theory. You end up with some nice thing that does interesting stuff, but has completely the wrong properties to do what you wanted it to do. Mm-hmm. So what's kind of happened is that this kind of holographic principle. What people have done is they've kind of said, okay, well, we don't know how this works, but let's assume it does work. Let's assume there is some kind of M theory or whatever. There's some kind of gravity theory which is going to and it's going to give us a gravity, and we have this duality, and so we can make statements about quantum gravity based upon what's happening at the boundary, based upon the gauge side of it. And so can we use this to understand things that we don't really understand about quantum gravity, like what happens when black holes evaporate and this kind of information paradox. So there's been this huge program to kind of try and do this, but it's a very strange program when you look into it, because they don't actually have a theory. They just have, we got this principle and we have one example of where it works, and we have some toy models where it works, and but let's kind of use this to explain paradoxes of quantum gravity, but we don't actually have a theory of quantum gravity. So it's a very, I don't know. And then you end up with people then having long arguments about, does this really kind of explain where information might go when a black hole evaporates, or doesn't it? And there are these long discussions about this and about what it happens in these toy models in 1 or 2 dimensions, it's to me a very frustrating kind of to try to follow, because you're like it's kind of the problem mathematicians have with physicists, but squared. I mean, you pick up these theories by these papers by Susskind or something about this, and where he was talking about this, and you kind of, it's not just like a normal problem with mathematicians have where you can't tell exactly what this person is saying. It's like they don't know what they're saying. I mean, they're making a huge set of assumptions about what might possibly, about what some mystical theory might have certain properties, and they're not writing down any of these assumptions. It's totally unclear which assumptions they're making, and then they're pursuing various calculations based upon totally impossible to figure out assumptions with no evidence for them, and it becomes a very weird subject to try to follow.
Yeah, I don't think that you have Susskind in mind for this, what I'm about to mention, but there's sort of an analog to the Sokal hoax that you write about in your book that I think connects nicely to this. I mean, you just made a sort of local criticism of the string theory literature, but in referring to Suskind's papers on the holographic principle.
Yeah.
But what is this hoax that you wrote about in Not Even Wrong, about two European brothers who wrote to you? And I think this says something about the literature on string theory. Not all of it, naturally, but some of it.
Yeah, so this was the Bogdanovs. Yeah, that was, yeah, so it wasn't, so this was after the Sokal hoax. So, I mean, anyway, just it kind of came up, people started talking about it and say, oh, there's kind of a physics, in the physics world, analog of what happened with the Sokal hoax. The Sokal hoax was done to philosophers, and so, and it was,
philosophers of a certain sort, I will say.
yeah, not to, but yeah, so philosophers, Sokal had taken in certain philosophers with some, by writing this nonsense paper, and so these brothers had written several papers, and anyway, so initially there was kind of a rumor, which was that this was a hoax and this was all an obvious fraud, and if you looked into it, it turns out they were the two brothers. I mean, they're really fascinating characters, and they're a long story, but they had gotten in, they had actually decided to try to get degrees in theoretical physics, and they'd then written their theses and some papers, and I think in retrospect it's just, these were just kind of really bad. It was kind of really bad work of a sort that it's again this problem that they didn't understand really what they're doing, and so they're just kind of talking about a lot of stuff they don't understand, and they write these papers which you kind of can't really make sense of, and you might at first think, oh, well, I'm just kind of being dumb. There must be something going on here. And then after a while, you realize it's just the author didn't really know what he was talking about. But the reason I wrote about it was some of these papers were published in quite reputable journals. And so I was kind of pointing this out as an example, is how do you tell the difference between work which really is consistent and makes sense in this kind of very speculative area, and then work which just kind of is complete nonsense, which even the author doesn't know what he's talking about. And
Clearly,
referees for certain well-known journals were not able to do this.
Right.
I mean, had been not, they just so the Bogdanovs had actually kind of demonstrated experimentally that this is, which was also in some sense what kind of Sokal was trying to do. He was trying to demonstrate that these people didn't know what they were reading and didn't know what they're talking about. But I mean, I think it was an even stronger thing than the Sokal hoax. In the Sokal case, you could say, well, Sokal was just being mean. He was setting up this thing specifically to fool them. The Bogdanovs, I think, they were genuine. They thought this made sense too.
I don't know. I mean, you received a bunch of emails from various places claiming to be like institutes in Europe, but you were able to trace the IP addresses because you're a computer wizard apparently, and you were able to figure out that they were all coming from the same place. So I don't know. That seems like some nefarious activity.
Well, they're not these people. They're not straightforward guys, but I don't think that they set out, oh, we're going to write complete nonsense and fool people. I think that they actually had some belief themselves that this, what they were doing, it was actually made sense. But yeah, they were, anyway, these guys, that they were kind of con artists, and they're certainly con artists.
Before we move on to some of the other problems you've identified with string theory. I am curious, most people do not take their jobs so seriously that they would write a book about why the field has gone astray and keep up this blog for 20, I don't know how many years you've been running it. But most people just clock in and clock out and they hate their jobs and they want to get out of it, but they don't talk about it so much. And I'm wondering, is it just you take physics so seriously, you really want to get the answers to these questions, that it frustrates you when you see the community going in a direction that you don't think is consonant with the spirit of the endeavor?
Yeah, I mean, that's right. But I don't think that's actually unusual. I think most people who do this or think about this stuff, it's not just a job. I mean, people get into this because they're really fascinated by this. And
so you think that's part of physics?
Yeah.
I don't think that's the same with accounting.
Yeah, no. So I think, I take most, academic physicists doing research at the Word, they really, they're just fascinated by these questions and they're trying to figure it out. They want to do everything possible to do it, and what they're doing what they do because they believe this is the best thing to do. And there are a couple of reasons I wrote this. I mean, one, there's certainly throughout the 90s, I would describe myself as, in the 80s, I was kind of more in mode, okay, well, people can do what they want to do. I don't believe that, this is fine, but I think it's going to blow over. In the 90s, I was becoming more and more disturbed by wait a minute, why is this not going away? It's just, this just is not working. It's clearly not working. And then why is it just getting more and more attention? Why are there TV programs about it? Why is it doing this? And, somebody should explain what the problems are here. And it's the kind of thing that it's actually a complicated enough story that I think it actually really requires kind of a book-length thing to really kind of get into it, explain what is going on. I mean, people like to have kind of a pro and anti-string theory arguments, which are, based on sloganeering, but it's a very complicated story. And so I wanted to, and I also thought it was an interesting one. I thought it was also interesting to tell it from a point of view that was more about the mathematics about it, because anyway, there's a really interesting story about what the role of mathematics is played in this, and it's played in general. And so, and I think I came from, so I had kind of an unusual perspective, I realized, for a couple of reasons. One is, I was working in a math department. I had really kind of understood a lot of this mathematics and how mathematicians thought, so I had a different perspective on it. So I could write about that. The other thing, honestly, is that there's actually a really unpleasant atmosphere of kind of intimidation that had come about because of this, that it had become kind of an academic controversy where, people were really loath to kind of say what they thought because that this could carry serious implications for their professional career. And just, that there are all these people saying string theory is the most wonderful thing. And, the whole story, there's also kind of a political aspect to this, that, in every department from 84 on, there were people pushing string theory. There were physicists who thought, well, string theory isn't really physics. Let's keep these people out. So there was a real, often kind of academically brutal fight going on between people who wanted, let's hire string theorists, let's do string theory, and people who were opposed to it. And, so I think, Glashow, for instance, seems to have been kind of forced out by this and left Harvard and went to BU. I mean, it was, and so when I would talk to people in private, I'd find that, a lot of people had no trouble agreeing with me, saying, yeah, you're right, there are all these problems, but, I'm not going to say anything publicly because that's going to get me on the wrong side of all these powerful people who are going to be annoyed at me, and, I just can't do that. I can't do that for my own ability to get a grant and for ability to get jobs for my students. I just can't do it. And I was thinking, okay, well, I have this weird position in a math department. I'm out of this. I can say what I think without having serious professional implications about it. So maybe I should be the one to do it. And that's one aspect. That's another aspect of the motivation. Besides, of course, it really was things I had deep opinions about and strong opinions about, and I thought there is kind of a clear story about what's going on here, which is not getting attention, and a point of view which is not getting said for various reasons, and I should do it. And I mean, Lee Smolin, though, was having, I think, some similar thoughts from a different point of view, and that's why he ended up writing his book around the same time.
Mm-hmm. Did you end up suffering any job consequences with your job?
No. I mean, I have to say I've always gotten along very well with the people in the math department. They've always treated me extremely well, and and that remains true to this day. And they were so mathematicians and also kind of see this with a little more of a bemused attitude. They're like, why are these people why is this going on, and why are people so excited about it? There's interesting math coming out about it. That's good. And so why does anybody care? And so they're just kind of more kind of like, what's this about? And then they're kind of interested to hear about it, but they don't take any of it personally. It's not like this is some one side or another is a threat to me.
Well, Brian Greene is obviously one of the world's most famous physicists.
Yeah.
Is Columbia's physics department predominantly string theorists in the high energy particle physics sector?
I think more so. Well, I wouldn't say so. I mean, they've had they have some string theorists, some non-string theorists. So there's they're like most departments. There's a wide variety of things going on.
But you were fine with the physics department too.
Yeah, I've had the problem. I mean, I'm not kind of sad about this. That I think the directions in which they've gone. Some of it is string theory. Some of it is other directions, but they're not. They've generally gone in directions into things which don't. I mean, ignoring me personally, maybe a thing to say is there's actually very, very little interaction between the math department here and the physics department. There's really, mathematicians don't go to physics talks, physicists don't show up at math talks. Actually, when Brian, when he first came, he actually had a joint seminar between the mathematicians and physicists, which actually was great. But that kind of ended after a while. And Brian then kind of moved mostly over to the physics department. He's mostly been there, and he's kind of lost most of his interest in mathematics and is more interested in physics and philosophy and other things. And so I would just say, just in general, it's sad, both here and also more from the field in general, just how the subjects, there have been times when they've come together and really interesting things have happened, but it's kind of come apart now, and it's just not happening now. And so personally, I'm sorry I don't have more interaction with what's going on with the physicists. And some of it's because some of them are working on string theory, not interested in, but other people are doing other things, which it just doesn't happen to have anything to do with what I'm working on. So I hope this will change someday.
Yeah. Well, in the time remaining to us, I'd like to return to because there are still more issues with string theory that we haven't talked about. One of them is what's known as the String-Theoretic landscape. And again, this is one of those concepts where as a layperson, it can be explained in such a way that it feels very promising and exciting and like it's solving a lot of really big existential questions. Yeah. So I'm curious to hear how you'll describe what the landscape is and why it might not actually be a good thing. Yeah,
I mean, I have kind of the opposite point of view on it. When this idea first came out, So to go on about what the idea is, so the one problem. So there's this problem. Okay, what do you do with the 6 dimensions? And the initial hope was that, well, maybe there's just a few possible Clabauts, and we can just find a few possibilities and find one that looks like a real world. But then what you found is that all of the simple possibilities that you looked at didn't look at all like the real world, and in particular, they don't have a positive cosmological constant. So one example is that the things that you looked at in ADS-FT have negative curvature where you want positive curvature. So trying to find consistent versions of things to do with it with the 6 dimensions where you had positive curvature and you could explain the cosmological constant. Groups of people finally came up with some ways of doing this, but it was kind of a Pyrrhic victory though, because what they found was that not just one or two ways of doing this. They found, some exponentially large or essentially infinite number of possibilities. And so you can think of these possibilities as embedded in some infinite dimensional space of the landscape of all these possible constructions. And so Susskind then, so my reaction when I first heard this was, well, okay, well, this is the end of it. I mean, once you've decided that your theory doesn't have, your theory actually kind of can't calculate any of the things you wanted to calculate because there's this infinite number of possible things consistent with your theory, and they all have different physics, and you can make them look like whatever you want. You now have an empty theory, and you're done. So you got to quit, go home, and say, well, let's do something else. But instead, there was this weird thing that Susskind was one of the great promoters of this. It's like, okay, well, this is great. It's like, we don't. Okay, the fact that there's an infinite number of possibilities, well, within this infinite number of possibilities, there's probably us somewhere. And so the explanation for why us is not something that we can ever calculate because we're just at a random place, and different big bangs will lead to different possibilities, and our big bang just happened to lead to this one, and we can't ever really explain anything about ours, and so we just kind of give up on that, and we just say we've explained it. And so, I mean, to somebody who is not used to thinking about these things, you can make this sound like, that this is an explanation of some kind, but it's not. It's not a scientific explanation. A scientific explanation, you're supposed to say, here's a way to actually calculate something about the real world, and if you go out and check it, you can check it and see if your theory is right. This explanation, it's completely non-falsifiable. It's like a religion. It's like, could be true, could be not true, but there's nothing that any of us can do that will ever provide evidence for or against this. Mm-hmm. So it's just not. I would say it's pretty clearly not science, and so. Then there was a big argument in the late 2000s about is this even really physics or not? And to this day, I think there are people who. I still kind of think the argument that this really isn't physics. You can't do that and claim you're doing science. Actually, has kind of carried the day. Very, 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 very few people actually do this. Some people use it as kind of as an argument justifying why you should still do a string theory, but the number of people out there kind of trying to calculate anything about the landscape is pretty small.
Mm-hmm. Yeah. You mentioned the LHC, and that maybe we would come back to it. I mean, one of the really big promises of the LHC, beyond the Higgs boson, which was successful, was finding these superpartners. And superpartners have notably not been found. And one of the explanations for this is, we just don't know where we are in the string-theoretic landscape, and the energies at which we would be able to find superpartners is just much higher than we had anticipated. And in this way, it is able to avoid falsification by relying on the landscape idea.
Yeah. So So this is, I think, one thing. Maybe to begin is, I really want to say what I found disturbing about what's going on now. I think that what happened with supersymmetry is one important aspect of it. So as I said, I was never a big fan of these particular supersymmetric models because, anyway, because of the reasons I explained. And so, but the people who are doing string theory, the strings that they were working with are so-called superstrings. They have these anti-commuting variables in them, and they would naturally produce. And they have this property of supersymmetry. So if you look at them if you make the strings very, very small, if you look at them at large distances, you should expect to see the evidence of the supersymmetry and the superpartners. Again, they've got the problem is that. So naively, these superstring theories predict, every partner will have a superpartner, the thing you don't see. So there was a belief among a lot of string theorists that, the LA at the mass scale that's going to govern, the splittings between these partners and the super partners is the mass scale of the Higgs. And so the reason we haven't seen partners and super partners yet is because we haven't gotten to a high enough mass scale yet, high enough energy scale, that we can actually see these mass splittings that correspond to the Higgs kind of mass splitting, 100 GeV kind of mass splittings. And so it was a little bit, if you believe that, there wasn't really a good explanation why you weren't seeing things at the previous generation of experiments. So like at the Tevatron and in the 1990s, you should have actually seen something. But what was clear is that if you believed that story, okay, maybe you wouldn't see anything at the Tevatron, but you had to see something at the LHC. So there are all sorts of popular articles and books and papers written saying, okay, if this picture is right, maybe we'll see something at the Tevatron, but we'll definitely see it at the LHC. Mm-hmm. And then just one example, after I wrote my book, there was a fairly negative review in some major publication that said that, Woit just doesn't know what he's talking about because, he says string theory makes no predictions, but it's well known that string theory predicts supersymmetry and it's going to be tested at the LHC. And okay, I said, okay, well, great. Well, then, so my thought when I wrote the book was, okay, well, once the LHC comes online, if, either I'll be wrong and you'll see these super partners and then, okay, I'm completely wrong, these guys were right. Or, you won't see any super partners and then people will just have to acknowledge that we've told the world that we were going to see super partners, they're not there. Standard way science works, we were wrong, this theory is wrong. But I think I would say the most disturbing thing I've seen in recent years is that I can't think of a single string theorist who actually has, even among all the ones who were going on and on about how string theory said you're probably going to see these things at the LHC, none of them, not a single one, after you didn't see this, took this to heart and said, okay, well, I guess I'm wrong and I should do something else. And I think that is kind of part of what I find disturbing about what's happened in recent years. It's just kind of the whole subject has become kind of completely divorced from any kind of normal way in which science is supposed to work. It's become a very strange subject.
Well, I'm going to give voice to a sort of naive response to this, and I wonder how you'll respond to it. And what I have in mind is, okay, we've reached a point where, with the standard model, theory can respond to everything that we can throw at it as experimenters. With the LHC, given that, what are theoreticians, particularly quantum gravity theoreticians, supposed to do, if not proceed with theory that just can't be confirmed by experiment?
Yeah, no, that's a good argument, but it's also it's in some sense also not a good argument. It's like, okay, you're telling me it's not an argument that I want to keep doing these calculations that don't work, because anyway, that the strongest argument for that has always been, I'm going to keep doing those because I don't know of anything better to do. And that's in some sense what's driving the whole field at this point. Is like, yeah, okay, these things don't really work, but instead of doing the thing you're supposed to do as scientists, if something doesn't work, you admit it doesn't work, you internalize that, your field changes and people do other things. People are just keep doing the same thing, even in the full knowledge that this isn't really working. It's just not healthy. That's the first thing to say about it. And I should also say, one thing that I haven't talked about yet is that for many years, I was kind of more tolerant of this, and that I felt, okay, well, I don't have any great. I have some vague ideas about what people should do and what I think is interesting, and I tried to explain a lot of those, and not even wrong as time came out about say something about that kind of indicated what those were. But that those they haven't, my ideas haven't really worked, so I can't complain to these people that they're working on ideas which don't work, because I'm still working on my own ideas which don't work, and it's fine. But in the last few years, I've actually found some of the ideas which go back to when I was first a postdoc. All of a sudden, I've realized these things which I thought really just couldn't possibly work, all of a sudden really, there's something going on there. They actually do work. So I've actually gotten very excited about some of my own ideas about, has to do with the geometry of spinners and twisters, and it's a whole nother story. But I found that it's very hard to even talk to anyone about anything except string theory and what these people are doing, because people have spent 40 years doing this, and there's like 3 and 4 generations of students who've been trained in a certain worldview, and I've always thought, okay, first thing you got to do is to get them to realize that this worldview is not working, and then maybe you can start talking about more interesting things. But it's become more and more disturbing the extent to which people have really dug into this worldview of what's going on with these theories, which has no evidence for it. It just doesn't work, but they're just going to stick to it because they don't. And you can't. Part of the implication of this is you can't even begin talking about other subjects to them, because they're convinced that that's all old story, that's all dead. The path that we took down here is not just a long path down a blind alley. It's the only possible conceivable path to progress, and that's the attitude. And I just have to say the single thing I found most disturbing in recent years is watching very smart people I know, and very just kind of really digging in and really kind of refusing to admit that something that's obviously true is true, and it's kind of disturbing to seeing people, the way people will go on about string theory. Some of them, I mean, Andy Strominger of Harvard at some recent thing was going on about how string theory is a huge success, it deserves an A+++, and it's really not all right for people to be doing that. And I think it's gone past the point. So I'm actually at the point now much more disturbed about the whole thing, the whole story, than I was back when I wrote that book. I find this actually, even listening to some of what, I actually found myself getting physically ill actually listening to Witten and some of these other people going on about string theory recently, because it's just not. Anyway, I had a huge respect for these people, but watching where they've ended up is just not. It's just disturbing.
And is the reason that you feel worse now because the arguments have changed, or just because the arguments still stand and now it's been 20, 25 plus years and things haven't really changed?
Yeah, no, I would say, very simply, the arguments I was making in about 20 years ago, and not even wrong, have been, to me, they're just as, there's huge amounts more evidence for them now than then. And, and the reaction then of people, well, let's just ignore these arguments. And, I think there have been several very well-known physicists who when asked about not even wrong, they said, well, I'm just refusing to read it. And that's a fairly standard way of dealing with it. And they're still, 20 years later, they're still refusing to admit what happened. And it's just not, it's kind of really not all right.
So again, on the surface, as a layperson, the landscape sounds nice because it sounds like it solves the big fine-tuning problem. And when I asked Lenny about other possibilities beyond string theory for dealing with this issue, he said that occasionally people will post papers to the archive, but they all die after a couple of days because none of them have anything to them. None of the other approaches to quantum gravity have shown any promise. And this, I think, is just one instance of the only game in town argument being invoked. Granted that string theory does suck up all the oxygen in the room, and there isn't that much content out there relative to string theory about the other options, though I've had some conversations about causal set theory, for instance, on the show. What is the quantum gravity landscape like out there? as far as other approaches and their promise?
Well, I don't know. I mean, I think, to my mind, right now, I actually have a very specific idea in mind, which about this, and it's maybe one thing, maybe kind of a very simple way of saying it is that, if you go and look at the real world, you find that matter particles are governed by the Dirac equation, and they're spinors. So that.
Could you say what a spinor is for our listeners?
Well. The problem in some sense is that there isn't, they're not very intuitive objects. But maybe a thing to say mathematically is that mathematically we normally think about geometry in terms of vectors. And that's a kind of an intuitive thing. We know what a vector is. And so we're used to thinking about vectors and generalizations of vectors and stuff like that. But what was realized by mathematicians and mathematicians early on, partly motivated by seeing what was going on in physics, is that you can think of, there's something in some sense more fundamental than vectors, that you can think of vectors in some sense as products of these two things called spinors. And anyway, it's a quite mathematically quite intricate story, but there is a kind of a well understood way of thinking about geometry where vectors just are not fundamental, spinors are fundamental, it's really hard to say what a spinor is, except it's a square root of a vector. It's something that you can, but it really is more fundamental. And I would argue that one of the thing which has really gone wrong with quantum gravity is that people have not thinking about it in terms of spinors. I think that there is this more fun. They keep talking about we're going to get rid of geometry and replace it by something new, but they're not really realizing that there is already something different, more fundamental than regular geometry with spinors. And there's some, anyway, so I think there's all sorts of interesting things to do there. Some of these things actually go back to what people did when they started to do loop quantum gravity. Some of the motivation of loop quantum gravity anyway, Ashtakar's variables are most naturally understood in terms of spinors. So there is some kind of history of it there, but it's just very different than what's going on. And so I really don't, anyway, I think there's a lot of interesting ways of thinking, possible new ways of thinking about gravity in this direction, but it's completely, it's completely different than what, where the field has been going, and there's this huge effort of people working on quantum gravity, but it doesn't. To my mind, it's kind of gone nowhere, and it doesn't really kind of connect to the standard model, and it doesn't connect to mathematics, which I think is interesting. But I think Susskind would just say, oh well, Woit, he's just another one of these guys who's has some idea, and it's going to go nowhere, and we're never going to hear about it, and anyway, so, but a lot of, what I'm working on, I'm very excited about, but people are always excited about their own ideas, even when they're wrong, they may be wrong, but it is really disturbing just to see very directly how dug in the subject has become in this one failed direction, and when you start to try and talk to people about something different, you start to realize it's like, people just don't, are just not used to thinking about anything else except this point of view. And from this point of view, what you're saying is just a foreign language, which doesn't make any sense. And it's, anyway, and that's kind of where we are.
How given the sorts of things we've talked about, such as the unintuitiveness of 10 extra dimensions, the super partners, the landscape, how is it that string theory came to so dominate the high energy particle physics landscape to the point where any other approach can't really even get off the ground, it seems?
Well, I think
Witten, these big titans might play some role. That's one of the reasons why
I think Witten personally has something to answer for there, but it's more generally, if you look at the sociology of how progress gets made and how progress was made in healthier times, it's always been a subject that's very kind of very faddish, that everybody is always kind of, it's very, very interesting to me to contrast it to mathematics, which I now know very well, which has a very kind of different sociology. And in physics, in this kind of physics, everybody is always they're looking to the smart people and what is everybody else working on, and how can I write a paper somehow about that? And mathematicians have always, and I think what traditionally drove that was that, a new accelerator would start up, that it would see some completely new phenomenon. Everybody in the subject would kind of jump on the problem of how do we understand this new phenomenon, and then the person who first figured it out would get a Nobel Prize. And so, and that was the way you made progress. But in some sense, you've removed, what the problem with the subject is that you've removed the thing which was, providing oxygen and allowing this to work, which you've removed the impetus of new experimental results. There just haven't been any new experimental results in years. And so, but the same sociology of let's all look at what everybody else is doing and all try to find the one most promising idea and all together, work on it is really kind of the mindset of the subject. And I think, Lee Smolin, I think, was also very aware of this and has a lot of interesting things to say about this. But it's very, there's a certain, and then, when you understand how academia works, it's all, how do you have a career in the subject? Well, you have to get in the right graduate school, you have to write the right kind of thesis, you have to have postdocs. There's a certain kind of career path, and there are not that many jobs, and there's kind of one way to kind of successfully manage this maze and end up with a kind of permanent job you want. And that, the way things are set up, it's very unclear how you can do that without following exactly a certain fad, surfing the right fad at the right time, and just deciding I'm going to go off and do something orthogonal to what these standard programs and fads are, is just, it's really kind of career suicide if you would try to do it in most academic. So I don't know if that is really an answer or not.
No, it's helpful. But now towards finishing up, wrapping up, what does it mean to say that string theory is not even wrong, and where does that come from?
Yeah, so the history of it, so this was often attributed to Pauli, that it was something that he was known to be very critical of things and to say, at a talk, this is wrong, this is completely wrong. And supposedly late in life, he was asked by somebody about some paper, and he shook his head and said, "Oh, well, that one's not even wrong." And you could take it as a really somewhat nasty and aggressive put down, is that's so bad it's not even wrong. But there's also another meaning to me has always been that whenever people are working on speculative ideas, they're always not clear whether they're right or wrong. And then the whole point of the thing is, how do you get some idea to the point where you can tell whether it's right or wrong? And so not even wrong also kind of applies to, most of my own work, or most of what everybody is doing in this subject, and how you kind of, how you emerge from that into something which can be right or wrong is not so clear.
Mm-hmm. Is it fair to say, in string theory's case, maybe it's, I want to be impartial, not necessarily my words, because I'm also not in a point where I can truly evaluate both sides with the expertise of a physicist. But the idea is that, on the one hand, it is so incomplete. Witness M theory is not completely formulated. It can't really and hasn't made experimental predictions, though, of course, people hope maybe they'll look up and see a cosmic string, but that's really just a wish. So that's one thing, but then on the other hand, it's not even wrong because people won't admit that it's wrong.
Yeah, well, no, but that's actually, I think I've become much more, now I'm less fond of that phrase than I was when I wrote the book. And I would actually argue that it's the situation is different now, and this is actually what's upsetting to me. That this is an idea and a research program that has moved from a standard kind of speculative area that we're trying to figure it out and we're trying to see what its implications are, and it's not even wrong in that sense yet. To this point, this is actually now wrong. This is just wrong. I mean, I'm sorry. This is just actually, the evidence is overwhelming. This is actually a bad idea about physics. It just does not work. And 40 years of ideas of work have shown exactly why this is true. And the situation of really smart people publicly kind of denying this is disturbing. It actually makes me physically ill. I'm sorry. That's where I am really now. So I'm kind of moving. That's a way of saying where I moved. I moved from, this is about not even wrong to this is about, something which really is wrong, which people won't admit it.
Mm-hmm. And maybe you'll have a gloomy outlook on this question, but what do you think is going to happen if you were forced to make a guess about string theory and high energy particle physics going forward?
I don't know. I mean, I think it's kind of, well, I mean, you can see that the forces on it. I mean, one thing is that, money is always drives it a lot. And a lot of the money is now coming from AI. So, people are just going to take what they're doing and start to claim that they're using AI to do it more. And AI can do meaningless calculations as well as people can. So I think there's a kind of a depressing, anyway, it's kind of depressing to see where the pressures from funding are kind of pushing people and where they're likely to go, and it's nothing good. I mean, the weird thing about all this is that personally, these ideas that I'm playing with, I mean, they look more and more promising. I'm having fun. I can see a lot of things to do, so I feel kind of great personally about my own personal situation, my own life, and what I'm doing every day. This is great, but seeing what's happening with the rest of the field, it doesn't seem to be going well. There's something I was actually thinking about this morning. I was just reading an article about what's called model collapse in AI. That people see what happens if you have these models which are trained on certain data from the real world and from people, and they become more and more adept at actually being more and more like people and saying non-trivial interesting things. But then what if they start you start running out of that data from real people to them, and there's just more and more AI generated data in the world, and that starts getting fed back into the AI. And what you see very quickly is you see a collapse of the model. The model kind of, if you start feeding it its own output, it just starts producing things which just are more and more meaningless, and just there's a well-defined sense in which it collapses. And I'm actually kind of thinking there is some aspect of that's happened to the physics community, the physics theory community. It's kind of, for 40 years it's been producing this stuff, and it's now 40 years of not just producing it but feeding it back to itself as this is what good physics looks like. And you have there is a sense in which the subject really can kind of have kind of an intellectual collapse because of just being it's set up to take certain kind of inputs and to do certain kinds of things with them, but if it's kind of polluting its own inputs, and it's just going to get worse and worse.
Well, Peter, it has been an immense pleasure talking to you, and I really appreciate all of this work you've done. I know that you didn't actually suffer any professional consequences from it, but it's still a bona fide dissident activity, and it really benefits the lay people like me to get both sides. So thanks again.
Okay, well, thank you.